Welcome back to this module on exploiting TLP to improve the throughput of a single core. The topic of this lesson is block multithreading, also called coarse-grained multithreading. The basic idea behind coarse-grained multithreading is very simple and is very similar to software multithreading. Each running thread executes until it blocks due to a long latency event. So it's very similar to software multithreading, but at a different scale because a thread switch is much faster than a process context switch. In these figures here at the bottom, I try to illustrate the execution of a program on a superscalar processor. If we execute only a single thread, then we will see that if we have 4 issue slots, which are illustrated here by boxes, corresponding to an instruction can be executed on a functional unit during a particular cycle, and vertically we show the cycles, then we will see that there will be many issue slots, the white boxes, wasted, because either the processor, the instruction is waiting for its operand, or the processor is stalled altogether because of, for example, a data cache miss, right? In a block multi-threaded processor, we try to fill this waste, called vertical waste in the famous paper by Toulson, meaning none of the issue slot is occupied, by a different thread. We discover here after a certain number of cycles that the blue thread, thread 1, incurs a cache miss. Then we need to flush the remaining instructions from this thread. Of course, there is a cost involved with that. And then we start executing threads from another ready thread, in this case the green thread corresponding to thread 3. And that's how we fill some of the white boxes corresponding to execution cycles. Let me now illustrate how block multithreading can be implemented in our canonical 5-stage pipeline. It's not the best way to implement multithreading in a single issue 5-stage pipeline, but let's see how the pipeline differs. First, we see on the left that we need at least 2 program counters, right? Because we need to be able to fetch instructions from different threads. Then the thread selector, shown here at the bottom, selects from either the program counter of thread 1 or the program counter of thread 2 and sends it to the instruction cache. A miss in the level 1 cache triggers a context switch. So we see that the miss signal of the instruction cache as well as the data cache are fed into the thread selector, because this allows the thread selector to put aside this thread to allow another thread to run. The instruction cache remains identical. It stays absolutely the same, right? Perhaps we need a bigger, because the working sets of both threads needs to fit in the instruction cache, but basically the structure is unchanged. However, the instruction translation look-aside buffer must include the thread identifier, because the virtual to physical address translation of the 2 threads are not the same. Virtual address 10 may map to physical address 100 for thread 1, and it may map to physical address 1000 for thread 2. So the instruction translation look-aside buffer needs to include the thread ID somehow. Notice also that the register file is split between the threads. This can be done statically or dynamically depending on the requirements of the threads, but this mainly applies to simultaneous multithreading. For the instruction decode stage, we need to replicate the register file. This might have an effect on the register file latency. The execute stage stays exactly the same. We have one ALU which is shared, but in a time shared manner in different cycles between the 2 threads.
And the iCache or data cache miss raise a hardware exception. Furthermore, the instruction cache and the data cache have to be lockup free. That means we need to be able to deal with two cache accesses, to handle two cache accesses at the same time. One may be a hit and the other may be a miss, or both threads may have missed, because here I assume that we have two hardware threads and we must be able to support two misses at the same time. Finally, the write back. If there was a miss in cache, the hardware exception is taken. That means the instructions that are currently in the preceding instruction fetch, decode, execute or mem stage are flushed, and the thread selector switches to the other thread. But this may also occur already before if we interrupt the current instruction.
This completes this lesson. Thanks for watching. In the next lesson I will give some examples of block multi-threaded processes. Hope to see you back.